Hello and welcome to Moxa's webinar, Wireless Options in a Changing World. I'm Martin McHugh and I'll be your moderator today. If you have any questions at any time during the webinar, please use the questions pane by simply typing in your question and clicking send. At the end of the presentation, we'll do a Q&A, take as many questions as we have time for, and we'll follow up with any unanswered questions after the webinar. All right, let's get started. We will have 30 to 40 minutes of presentation with 15 to 20 minutes of Q&A. Today's presenter is Ariana Drivdahl. Ariana is the Product Marketing Manager for the Industrial Wireless Group here at Moxa. With that, I'll hand it over to Ariana.
Thanks, Marty, and hello everyone. Thanks for joining our webinar today. As Marty mentioned, we're going to be discussing wireless for a changing world. We've got some great information for you guys, so again, appreciate the attendance, and we're going to go ahead and get started. This is what we're going to talk about today. We're going to get started and tell you guys about some of the common industrial wireless protocols that you may see on the market today. Then we're going to move into selecting the appropriate wireless solution for your application. And then we're going to do kind of the two primary focuses of this webinar, and the first being 802.11 or Wi-Fi. So I'm going to go ahead and give you guys an intro into the basically alphabet soup, as you will, a family, intro into the family of protocols. Then we'll move into special considerations for deploying your wireless installation. And then we're going to move into the other major focus of this webinar, which is going to be cellular technology. And I'll give you guys an intro into cellular technology and talk about kind of the differences between the different types of cellular networks and which carriers support each type of network. That is a pretty important distinction when you're talking about cellular technology. And then finally, we're going to talk about how you can help to ensure constant cellular connection to your devices when you're doing remote monitoring. As many of you know, cellular tends to disconnect and reconnect occasionally. And of course, when you're trying to monitor devices, that definitely makes for a little bit of a difficult situation. So I'm going to talk about some of the options that are available to you with that. So we'll go ahead and get started. There are many different types of wireless technologies that are available on the market today. Not all of them are going to be appropriate for industrial use, but some of the ones that you may see out there are things like Bluetooth, Zigbee, 900 megahertz, Wi-Fi, and cellular, as well as wireless HART, ISA 100, and some of the other various smaller standards. When we talk about industrial wireless LAN, we tend to kind of focus on two different regions as the primaries. The first one being what we call a wide WAN, which is pretty much cellular and can also encompass Wi-Fi. And then we also talk about WPAN, which is more of a personal area network, and that encompasses things like Bluetooth, Zigbee, and infrared. And each of these definitely have their place within the industrial space, and they also each have their own pros and cons. So we're going to kind of go through them and talk about which might be appropriate for what types of applications. So Bluetooth, as I mentioned, is a short-range wireless network. It's used to create what we call PANs, or personal area networks. And what that means is it has a very limited range. So, you know, when most people think about Bluetooth, they think of things like their cell phones, perhaps their laptops. Bluetooth technology is typically present in cars to connect, you know, phones or other devices. So we typically see that a little bit more in consumer use than we do in industrial use. And one of the big reasons for that is that the range is typically very limited. It's typically 30 feet is about the most that you're going to get. And of course, when you're talking larger industrial installations, that range tends to not be quite enough. Bluetooth does use 2.4 to 2.48 gigahertz as the frequency that it transmits on, which tends to be a little bit of an issue if you're using some of the Wi-Fi frequencies, which also operate in that same range. So it tends to have a little bit of interference when it's used in the same region or same area as wireless networks. Bluetooth uses what's called frequency hopping spread spectrum, or FHSS, for its transmission. If you're familiar with Wi-Fi, some of the Wi-Fi protocols use this as well. And Bluetooth is a packet-based protocol with a master-slave type of a topology. Now, Zigbee is quite similar to Bluetooth in terms of the range. It's also considered a PAN, or personal network, but Zigbee tends to be a little bit more of a robust protocol, and because of that, it's becoming a little bit more popular in industrial automation, especially for short-range communications. We've seen a lot of people basically taking out their RFID type applications and putting in Zigbee in place for that, and that just kind of modernizes some of the old communication standards that have been in place in these types of applications. The really nice thing about Zigbee is that the radios tend to be very low power. So if you've ever used any wireless technologies before, you're probably aware that most of them have a fairly decent power draw. And Zigbee is kind of on the very low end of that spectrum. So it's great for battery-operated devices or things that are remote and don't need, dedicated power supply or a large dedicated power supply. Zigbee also uses mesh networking, which means that if you have a cluster of devices in an area, they can all essentially use each other to communicate through each other. So if you have 12 devices connected, the first device in the mesh network can still connect to the last device in the mesh network, even if the two are out of range of each other. As long as they're within range of the actual mesh network, they will still be able to communicate. So it's a pretty neat technology. Zigbee does use a few different frequencies depending on where you are in the world. For those of you who have, who ship devices over to Europe, they use 868 megahertz over there. The U.S. and Australia, we use 915 megahertz here. And in most other places in the world, they use 2.4 gigahertz. And again, because Wi-Fi does transmit some of the protocols on 2.4 gigahertz, those countries that use that version of Zigbee can also have interference with wireless networks. So have to be careful about implementing those in the same general area. Zigbee also tends to be a very low transmission rate, so typically anywhere from 20 to 900 kilobits per second. So not good for any video or any kind of data-intensive transmission. 900 megahertz is another protocol that's commonly used. It's typically used in very long-range point-to-point type applications, so very similar to like a wireless backhaul. It's great for people who need wireless communications to a remote site, for example. You'll put a 900 megahertz system at each end of the site and have that site be able to communicate back through that 900 megahertz system to a central control room or anywhere where that data needs to go back to. Now, 900 megahertz is similar with Wi-Fi in the respect that the lower frequency range that it operates on, the greater the distance. So as you can imagine, 900 megahertz can go pretty far. There's people who do upwards of 20, 30, 40 miles with 900 megahertz. The downfall of that is that it tends to have very low bandwidth available. So most 900 megahertz systems, they're also proprietary, but they tend to top out at about 1 to 2 megabits per second. So it's also good for doing remote monitoring of data points or any kind of small bandwidth type of application. So again, not the greatest if you want to send video monitoring back across a long distance. You probably want to take a look at another type of backhaul communication for that type of application. Now, Wi-Fi, of course, is the most popular consumer and communication technology, both in the industrial and in the consumer space. It, of course, forms the bulk of what we're going to be talking about in this presentation, but there are a lot of different standards that are adopted through the development of Wi-Fi, and we're going to kind of talk about each one of those in detail. So, we've gone through kind of some of the more common types of wireless communications. So you guys may be wondering, well, what type of application, what type of communication protocol is right for my application? And for, the biggest thing is you guys have to decide, is it something that needs a long distance communication, or is it something that needs a higher throughput but kind of a shorter communication distance? So if you're looking at a very wide distance, whether it's, communicating to various roadside boxes across highways, whether it's bringing communications across an oil pipeline, whether it's communicating to power transmission towers. All these types of devices are perfect because they tend to be a little bit lower bandwidth, but they need great distances. So with those types of applications, you're really going to be looking at kind of a cellular or a 900 megahertz or a long distance type of a solution. On the other hand, if your application includes things that are, moving at a fast rate, for example, say an AGV within a warehouse, or they need high throughput, like you're transmitting video from a bus, or you're pulling data from, a fuel management system, these types of applications tend to require higher bandwidth, but they also tend to be a lot closer in terms of the communication distance. So for those types of applications, you're probably going to be looking more of a WLAN or a Wi-Fi type of an installation. So I'd like to ask you guys a question now if we can. What type of wireless have you implemented at your facilities? Wi-Fi, cellular, Zigbee, or I'm still working on detangling myself. And, we see a pretty good mix of different types of wireless technologies out there. They, of course, all have their pros and cons, but we see a surprising number of people who are actually still working on detangling themselves. So that's okay, too. That's actually great. We're glad to see those types of people on this presentation. Hopefully that'll kind of help educate you guys a little bit more towards what type of technology you're going to want to use in your application. But we've got lots of great answers coming through. It looks like Wi-Fi is taking the cake at the moment, but we're going to give you guys just a few more seconds to get your votes in. So if you haven't clicked that button, please do so at this point. All right, so Wi-Fi seems to be the most popular of the wireless communication protocols. 64% of you guys are using Wi-Fi. Cellular is third, fairly far behind. And of course, I'm still working on detangling myself. It's pretty close to cellular, which is great. Hopefully we'll be able to educate those of you again. And Zigbee, a few people here, it looks like, are using Zigbee. But that's great. So thanks you guys for voting, and we'll have a couple more for you a little bit later on in the presentation. So with that, we're going to go ahead and start and give you guys kind of an intro into the Wi-Fi family. So 802.11 alphabet soup. There are quite a few different wireless standards nowadays. If you're not familiar with them, it can seem kind of overwhelming and confusing, but there are really 4 main ones that you're going to want to take a look at or consider if you're looking at implementing Wi-Fi within your facility. So those 4 standards are 802.11a, b, g, and n. And of course, they all have kind of their pros and cons. So this chart gives you a quick overview of them. I'm going to go through all of them a little bit more in detail in the next few slides. So 802.11b and g is one that uses 2.4 gigahertz to communicate, which basically means that it goes a little bit of a longer distance, but it is also a little bit more susceptible to interference. So if you guys remember, I talked for Bluetooth and Zigbee. Both of those operate on 2.4 gigahertz as well. So they tend to be able to interfere with this type of application. So when you're using 802.11b and g, you definitely want to go into a location that has clean air, meaning there's not another wireless network, not other wireless protocols that are essentially operating in that type of environment. So one of the popular applications is a wireless backhaul. As I mentioned, there is basically an inverse relationship between distance and frequency. So the lower the frequency, the greater the distance you're going to be able to travel. So 2.4 gigahertz is great for wireless backhauls when you need a little bit more bandwidth than that's available with 900 megahertz. So in this example here, we've got some power distribution lines that also basically need to communicate back. So what we're doing is we're essentially taking a dual radio product and creating repeaters that are going to be installed on each one of these towers. And this type of application is replicable in many different environments, whether it's oil and gas, whether it's communication across transportation mediums. This is a very good example of what you would be using 2.4 gigahertz to do. It's clean space, it's got decent distances, and it still gives you kind of that great bandwidth. So even if you are pushing larger volumes of data through, such as video or a lot of data points, it's a great type of application for that. Now, some of the advantages and disadvantages of 802.11b and g. Of course, it is widely used. You guys all probably have a device, you're maybe even using one right now, that has support for these 2 protocols. 802.11g, in addition, is also backwards compatible to 802.11b, which is great because it allows good interoperability between older devices and those newer ones. And again, it also has that longer communication distance. Some of the disadvantages, of course, I mentioned the susceptibility to interference, and we'll kind of talk a little bit more about the different types of interference a little bit later on in this presentation. But in addition to that, it has what's called overlapping channels. And essentially what happens, this chart that you see on the bottom of your slide here is basically showing how the channels in 802.11b and g are laid out. And as you can see, they all kind of overlap with each other. And what happens is if you use those 2 channels that are, sit next to each other, they will cause interference with each other and either disrupt, decrease, or completely knock out your communication. So with 802.11b and g, you have to be really careful about what channels you use for installation to make sure that you're going to be able to have channels that don't overlap. So there's essentially 3 that you can use, and those are channels 1, 6, and 11. Now, even though those three channels don't overlap each other, you definitely have to be careful when selecting those, because if you have other wireless networks in the area that are also running BNG, typically they will tend to be on these three channels as well. So you always want to kind of do a site survey and take a look at which of those is going to be the least crowded, and that will typically give you the best results for your wireless network. 802.11a is a little bit different from 802.11b and G in that it operates on the 5 gigahertz and 5.8 gigahertz bands as opposed to the 2.4 gigahertz bands. So what does this mean for you guys? Well, it tends to be a lot more robust. There is not only is the way that the protocol is written is a little bit less susceptible to interference, but 5 gigahertz in addition tends to be a cleaner frequency. So there's not a lot of personal area networks. There's not a lot of other devices that can generate noise on that frequency. It tends to be just a better choice for harsh environments or environments that have a lot of either wireless noise or any kind of electrical noise that could also potentially interfere with a wireless network. So in this example here, the wireless devices are going to be installed on AGVs, which are moving throughout a facility. And they're basically communicating to access points that are going to be scattered throughout this major warehouse. And 802.11a is perfect for this, again, because you don't have to worry about any kind of electrical noise from the AGVs or any other devices that are going to be in the area. 5 gigahertz tends to be very clean. 5 gigahertz also tends to be very good in terms of bandwidth. It is max rated at about 54 megabits per second, so it is capable of transmitting some video over wireless if that's what you want to do with your application. So the advantages of 802.11a, of course, that less susceptibility to interference, but unlike 2.4 gigahertz, all the 802.11a 5 gigahertz channels are non-overlapping, which means that you can use the channels that are directly next to each other, and you don't have to worry about spacing them out or them knocking each other out like you do with 802.11b and G. In addition to that, the higher channels on 5 gigahertz, which is the 5.8 gigahertz band, are allowed to actually transmit higher power than the lower ones, so they're great for outdoor use. Some of the disadvantages of 802.11a, they do have a shorter communication distance, so it tends to be about 30 to 50% of the distance of 802.11b and G. So you can see that it is a pretty big decrease in terms of how far it can travel. And it's also not compatible with 802.11b and G. So if you're trying to do kind of a mixed network, unfortunately that's not going to be such a simple thing because those protocols don't play nice with each other. So you can see here the way that the channels are laid out with 802.11a. So you do see there are 3 bands. They're called the uni bands. Uni 1 is kind of the lower band that operates on a little over 5 gigahertz. And then Uni 2 and Uni 3 are going to be kind of the upper bands. And there are some special considerations for those upper uni bands, which I'll talk about in just a moment here. So when you want to get into using those upper bands, which a lot of people do because they're, they tend to be clean in terms of airspace, you have to worry about what's called DFS, or dynamic frequency selection. And basically what DFS is it's a technology that allows you to avoid interference with radar systems. So radar tends to also operate on the same types of frequencies as these Uni 2 and Uni 3 bands. And of course, we don't want to knock out radar because that could cause a very big problem to airplanes or any other kind of, anyone else who's going to basically rely on radar. So if you want to use those upper bands, you have to use a device that is, supporting DFS. And basically the way that it works is anytime you select those channels for use, those DFS channels for use, the access point will essentially scan to see if it sees any kind of radar signals in the area. If it sees any of those signals, it says, nope, I can't talk on that channel. I'm going to go ahead and change myself. And so it changes to a channel that does not have that radar detected on it. So all of the work basically for DFS is done, on the AP side. There's typically not any kind of setup that has to be done on the user level, but it is something that, you guys should be aware of, especially those of you who are operating facilities that may be close to, radar stations. So 802.11n is kind of the newest and most implemented of the wireless standards. It was ratified in October of 2009, and it was essentially drafted to address some of the bandwidth issues that we saw in 802.11a, b, and g. So of course, 802.11b topped out at 11 megabits per second. 802.11g and A topped out at 54 megabits per second. But really, when you got into kind of the nitty-gritties of the protocol and you know, determined your actual throughput, with those older standards, you were only looking at about half of what the theoretical max is. And that's just due to overhead and kind of the way that the protocol is written. So all of a sudden, you know, these great wireless protocols that were supposed to operate around 54 megabits per second, people were discovering were basically only functioning at like 25 to 27. And while that was good enough for the most part for a long time, people wanted to stream, for example, multiple video streams across their wireless network. You know, when you're talking HD or you're talking some of the you know, higher quality streams, that of course was not enough to keep up. So 802.11n was drafted. You know, there was a big push on the consumer side as well, as more people wanted to, you know, stream more and more devices across their wireless networks at home. So 802.11n basically works at speeds of up to 300 megabits per second, so it's a pretty substantial increase from the older standards. And it also works with gigabit Ethernet. And this is something that a lot of people don't think about when implementing wireless, is gigabit Ethernet typically tends to be required when you're doing an 802.11n installation. The reason for that is if you have only 10100 switches on your network, your wired network is ironically going to actually become the bottleneck for the wireless, just because 802.11n can go much faster than that. So if you are going to be looking at implementing an 802.11n network, you also want to make sure that you have the backbone, the wired backbone capacity to basically support it. So in terms of the industrial space, when we talk about 802.11n, we talk about high bandwidth applications. So you see here, this example is one where you basically have buses that have all been outfitted with Wi-Fi, and they record video all day long as they go across the routes. And that video can include, you know, things from inside the bus. It can include video feeds from outside the bus, and it all gets recorded essentially onto an NVR that sits on the bus. And at the end of the day, when those buses come back into the depot, they are all going to connect to an AP and transmit that video that's been stored in those NVRs back to a central control room so that it can be stored for safekeeping in case, you know, anything needs to be reviewed. This, of course, tends to be very high bandwidth because most of those files on the NVRs tend to be 1 or 2 gigabytes. So they tend to be very large files. And, of course, if you're using some of the older wireless standards, you would have a serious bottleneck in terms of, you know, how long it would take before you could get all those video offloaded. So 802.11n is the perfect example for an application such as this. But really, any kind of high data usage is going to, you know, you're going to want to take a look at 802.11n as the wireless standard for use. Now there are some advantages and disadvantages to 802.11n. I know that's hard to believe. Most of you guys are probably thinking, wow, 802.11n sounds awesome. It's super fast, but it does have some disadvantages too. So I kind of want to go through, you know, to be fair to the older protocols and kind of give you guys information on those as well. So 802.11n does have the ability to communicate backwards to all the 3 older standards, and that's 802.11a, b, and g. Now it's important to note, in order to be able to communicate backwards to these older standards, you have to have an 802.11n radio that supports both 2.4 and 5 gigahertz. So there will be some devices that operate on 2.4 gigahertz and only, or some that do 5 gigahertz and only. And in that case, those radios will only be backwards compatible to those protocols that have the same frequency. So, for example, if you have 5 gigahertz N, that radio will be backwards compatible with 802.11a, but not B or G. And conversely, if you have a radio that supports 2.4 gigahertz N, it will be compatible back to 802.11g and B, but not A. And again, we do have that high speed for 802.11n up to 300 megabits per second. And there's also technology built into the protocol that actually allows for the overcoming of interference. So we talked a little bit about, you know, Bluetooth and Zigbee and some other wireless noise potentially interfering with 2.4 gigahertz. 802.11n actually has some technology that will allow, you know, that to be reduced significantly. Some of the disadvantages, there are several draft versions, so you guys may have seen draft N, pre-N, some of these different types of notations. You have to be very careful when using those types of devices because there actually is a little bit of a difference in the final protocol from those draft standards. And if you're using, say, a final ratification AP, but you're using, say, a draft client, they may have some communication issues just because of that, the protocol being changed slightly. So you just want to make sure that you're using the same version across all of your devices. In addition to that, you have to use all 802.11n products in order to take advantage of the speeds of 802.11n. So we talked about backwards compatibility, and that's a great thing, but you know, unfortunately, when you do have that backwards compatibility requirement and you do have those older legacy devices that come onto your network, you will sacrifice the throughput because the system basically has to throttle back to those older protocols to allow them onto the network. And that's something that a lot of people don't realize when they implement ED. They think, hey, if I put in an 802.11n access point, all my devices are going to be able to communicate at 802.11n speeds. And unfortunately, that's not the case. So it's kind of a trade-off. You know, you have to think, do I want to allow legacy devices in terms of interoperability and kind of ease and upgrading, or do I want to have those full speeds of 802.11n? And that is something that, unfortunately, you know, you will have to make the choice on when you do a wireless N installation. So how does 802.11n do it? Talked about some of the great features of it, but at the core of 802.11n is a technology called MIMO, and it stands for multiple in, multiple out. And essentially what it does is it allows multiple streams to go across the antennas at the same time. So basically the more MIMO antennas you have, the more streams are going to be sent out. So for example, if you use a 2x2 MIMO system, this means you have 2 receive and 2 transmit antennas, and your data is essentially going to be split into 2 pieces, and it's going to be sent at the same time across both of those antennas. In the received end, it's basically going to recombine those and pass on the transmission. If you have a 3x3 MIMO system, meaning you have 3 transmit and 3 receive antennas, your data is now split into 3 pieces, and those 3 pieces are transmitted at the same time. So you can see that with each addition to a MIMO system, 2x2, 3x3, 4x4, you're going to be increasing your transmission rate accordingly, just because you know you have more antennas. So 2 antennas doubles it, 3 antennas triples it, 4 antennas quadruples it. The only downfall about MIMO is that you have to be careful when you have multiple antennas about the polarity. So if you don't have the antennas oriented properly, you're going to have them interfering with each other, which of course, you know, is something that you don't want in a wireless network. So most manufacturers have chosen to implement either a 2x2 or a 3x3 MIMO system, and that kind of gives a good sweet spot between having enough antennas to have, you know, a good MIMO system and a good bandwidth, but not so many that it makes engineering the product difficult in terms of the polarity of the antennas. In addition to that, the channel size for 802.11n is twice what it was in the older wireless standards. You can kind of think of that as a pipe, if you will. So if you have a pipe that's you know, a small diameter pipe, there's a certain volume of water that can basically flow through that pipe. If all of a sudden you double the size of that pipe, you don't have double the amount of water that can flow through. And it's the same thing with the wireless channels. When you have a small channel, you can have a certain amount of data pass through. When you double the size of that channel, you essentially double the amount of data that can go through it. So those 2 technologies, the MIMO and the channel bonding, are basically the 2 key reasons why there is such a high throughput for 802.11n. Now, I talked about this a little bit on the previous slide, but a special note, there are 2 different modes that you can use when operating 802.11n. They're called Greenfield and Mixed Mode. And I talked about how you need to use all 802.11n devices in order to take full advantage of it. And this is basically where you select what mode you want to use. So if you're using Greenfield mode, you're basically saying, I'm not going to allow anything except for 802.11n on my system. So even if you have older ABG products present within the wireless network range, they won't even be allowed onto the network. So if you select this mode, you're basically ensuring that you're going to get the maximum throughput possible with 802.11n. If, on the other hand, you say, no, I have a mix of older devices and newer devices, and I really need to make sure that all of them are going to be allowed onto the network and that they can all talk, you're going to want to set your device into what's called mixed mode. And again, you won't have that throughput for 802.11n, but you will have the backwards compatibility to allow all of those older devices onto your network. Now, I would be remiss if I didn't mention very briefly serial over wireless. Even though the trend is to go towards Ethernet-based networking, there are many, many, many devices out there that still operate on serial technology. And I don't want to forget about serial because, again, it is a very important part of wireless networking as well. There are many devices nowadays that actually can do serial to Wi-Fi, and they essentially work by creating a virtual COM port that's used, and that way you can basically access that device over a wireless or wired network. You can basically access that device as if you're physically plugged into it. So in this example here, we've got a CNC machine. Actually, two of them that are trying to communicate, and one of them is going to be doing serial to Ethernet, and one of them is going to be doing serial to wireless. So you do have the ability to do both of those, and again, it just kind of makes it a little bit easier to take a legacy device and bring it onto a modern network. So it's time for another question for you guys. So hopefully you all have your click fingers ready. I'd like to know what type of Wi-Fi you're using at your facility. So 802.11a, 802.11b, 802.11g, 802.11n, or serial over Wi-Fi. And if you don't currently use wireless, if you can just let us know maybe what type of wireless you would like to implement based on the type of data that we've had here in this presentation. So we've got some answers coming through here. It looks like it's going to be a little bit closer, this one, than our last poll. Right now it looks like 802.11g and N are the clear winners. Give you guys just a little bit more time to go ahead and get some answers in. All right, we do have some of the older protocols now coming in as well. It's good to see. We got to show the love for all of them still, because they, again, do have their place. But I think we've got some good answers coming in. So let's take a look at what you guys said. What type of Wi-Fi are you using? So our big winner here is 802.11n, but 802.11g is still pretty widely used, as is serial over Wi-Fi. So it's good to see that some of you serial guys are on here as well and are optimizing those devices into the newer communication mediums. 802.11a, surprisingly actually, only 3% of you guys selected 802.11a. It's actually surprising. We've been seeing we've been seeing a little bit more of a trend towards 802.11a and 5 gigahertz. So be curious to see if 6 months from now if that'll change at all. But thanks you guys for voting. We certainly appreciate it. And we've got one more to do a little bit later on in our presentation here. So some of the special considerations for wireless applications. You know, wireless is a little bit more difficult to implement than wired is, and the reason for that is there are so many different factors that can affect performance, that can affect throughput, that can interfere with a network. There's just a lot more to consider. It's not, unfortunately, as easy as plugging in a device and saying, yay, it works. So I wanted to just kind of give you guys a little bit of information on kind of some of the more common problems or special considerations. The first is security. You guys, I'm sure, all worry about security. We're seeing a big trend in networking towards, more and more secure devices, especially as we become more of a connected world. There's more of a concern over keeping data private, and wireless, of course, is one of the technologies that's most susceptible to being insecure just because everything that is transmitted, of course, is transmitted across open air. So if you don't have security, it becomes really easy to basically see what's transmitted across the wireless network. So you definitely want to make sure that you're securing your wireless network. And there's basically 3 types of security standards that you can use, and I'll go through each of them. The first and the oldest is WEP. This was kind of the first one that came out. It's supported across 802.11a, b, and g. But it's rarely used nowadays, and the reason for that is that the keys actually broadcast into open space. And unfortunately, I can't ask you guys to answer, but I usually like to ask people, if they can guess how long it takes to basically break into a WEP key, if you know what you're doing. And the answer, to most people's surprise, is a matter of seconds. So if you have somebody, if you are still using WEP, and you have someone that comes in that knows anything about wireless or wireless security, that essentially won't keep them out at all. So I tell people, it's better than nothing, certainly, but if you have the option for a better standard or a newer standard, you want to implement those as opposed to WEP. So WPA was basically developed in order to address the deficiencies of WEP. It does not broadcast the key into open air, so inherently it's more secure, and it's still used in a fairly good number of systems today. It's not considered hack-proof, but it is considered to be difficult to break into. So WPA for a lot of people is going to be enough. If, however, you want to get into kind of the ultimate or the highest level of wireless security, you're going to want to look at using WPA2. And pretty much all modern devices nowadays are going to support WPA2. So our recommendation, of course, is always to use WPA2 when possible. Currently, there is no security standard that's being developed to succeed WPA2, and the reason for that is that it's considered to be pretty hack-proof. It's very, very secure security standard. It's very, very difficult to break into. It's even used by the government. So I guess you can either say that's a good or a bad thing, but take that as you will. So WPA2 is the security standard that we highly recommend everybody uses when doing wireless networking. Now, the other thing to keep in mind is what type of antenna are you going to use? So wireless, again, has such a broad range of different types of applications. We really want to make sure that you guys are aware that different applications can use different types of antennas. So if you're doing what we call a typical AP client type of topology, which means that you have a point to multipoint, or you have one central access point that's allowing access to many devices, you're most likely going to want to look at what's called an omni or an omnidirectional antenna. This type of antenna broadcasts at 360 degrees, and then basically the radiation pattern looks like a donut. So this is the type of antenna that you're using, again, if you have many, many devices that are kind of scattered throughout your facility that you all want to have, give network access to. A semi-directive antenna, and I apologize, that picture actually should be for a higher gain antenna, but a semi-directive antenna is one that's kind of, it's a little bit of a curved disc, so it tends to broadcast from 45 to 60 degrees. And this is good when you have kind of clusters of devices that are all, grouped together, but aren't necessarily all around the central AP. So if you have, say, AGVs, several AGVs that are all going to be clustered in a specific area, you can kind of point that antenna towards that area, and it's kind of a sweet spot between an omni and a high gain directional antenna. So it allows you to kind of connect together groups of devices, but those groups of devices do have to be clustered within kind of the range of that antenna. The last one is a high gain or a directional antenna. These look exactly like you see in the picture. They're basically flat panels, and they're typically used for point-to-point or long-distance communication. So they tend to be very high gain. In fact, they allow Wi-Fi to go upwards of 10 to 20 kilometers in distance, which is not the distance you typically associate with Wi-Fi. But if you do want to go that type of distances, you are going to have to look at a very high gain antenna. And again, these tend to be point-to-point, so a one-to-one connection. So they're not good for many devices trying to have access. They're good for literally just bridging two remote locations together. So speaking of long distance, if you do want to have a long transmission distance for Wi-Fi, it is actually possible nowadays, which is great because there are a lot of people who use 900 megahertz who want some of those distances, but who also want some of the benefits like the security, the bandwidth that are available with Wi-Fi. So if you do want to go long distance with Wi-Fi, there are a couple of kind of levels, if you will, that you may want to take into account. If you're going to go anywhere from 10 kilometers and under, which is still a pretty good distance, typically all you're going to have to do is do some parameter adjustments within your communication devices, and some of them will of course have support for that built in. You'll also need some of those high gain antennas. If you want to go farther, so 10 to 20 kilometers, you're going to need a little bit more specialized equipment. So that includes things like either a higher powered radio module or some kind of a booster or a power amplifier to essentially bump up that signal to be able to travel that distance. And then of course you're still going to need those high gain antennas. So that's a little bit more of a tricky solution, but it is possible with Wi-Fi nowadays. Now, I want to spend just a few minutes talking about interference because interference is really kind of the bane of wireless's existence. And we kind of classify interference as basically any unwanted signal that degrades the quality of the wireless network. So there are three types of interference, or three classifications of interference. One is called narrowband, one is called broadband, and one is called co-channel. Narrowband is exactly what it sounds like. It's a very narrow band of frequencies, and it's not one that we typically worry about with wireless networking. Broadband and co-channel are kind of the two biggies that we always want to keep in mind when implementing the wireless network. So broadband is any kind of interference that comes from non-Wi-Fi devices. So this can be things like Bluetooth ovens, it can be things like cordless phones that operate on 2.4 gigahertz. Even microwave ovens, believe it or not, can actually interfere with wireless networks on 2.4 gigahertz. So we actually have had a few people who have tried to install a wireless network, say on the opposite side of a wall from a microwave oven in a break room, and not realizing the impact that that microwave, especially the commercial ones that are very powerful, can actually have on a wireless network. So when that microwave runs, it can knock out wireless completely, especially if it's running on 2.4 gigahertz. So those types of interference sources are ones that you definitely want to look out for when you're deciding where to install a wireless network. The other one is called co-channel interference, and this is kind of the most common interferer. And co-channel interference is basically classified as any kind of noise that's coming from another Wi-Fi network. So when I talked about 802.11b and G using channels 1, 6, and 11, if you have, say, 5 networks that are all running on channel 6, they're all going to have co-channel interference because they're all operating on the same frequency. And this can be very, very detrimental to wireless signals because if you have that many networks running on the same channel in the same area, they're basically going to knock each other out. So it's very important to note if there's any other wireless networks in the area, what channel they're running on, and you want to avoid those channels as best you can. Now, the way that you do that is by conducting what's called a site survey. And a site survey is something that many system integrators or many people just can do themselves. You basically use a tool. Some of them run on a laptop. Some of them are specialized equipment. But they basically take an inventory, if you will, of what's happening in the location of your wireless network. So they'll tell you if there's any electrical noise. They'll tell you if there's any other wireless networks, and if there's wireless networks, what channels they're operating on. And it'll basically recommend to you, what channel or what frequency you want to run your wireless network on, and that'll essentially help to make sure that you're running your network on the cleanest channel or the cleanest possible wireless space. And that's really key because the more interference that you have on any given wireless network, the worse the performance is going to be. And of course, nobody wants bad performing wireless. So we always want to make sure that we install on the best possible channel. PoE is something that's becoming very important as well. We've seen a trend in the last few years of more and more devices being powered by PoE. And this is great because it's a technology that allows you to basically send both power and data across one single wire. So for those of you who aren't familiar with PoE, there's basically two types of PoE devices. They're what's called a PSE, which stands for Power Sourcing Equipment. This is a device that can give power, or PoE power, to anything that's connected to it. Then you have what's called a PD, or a powered device, and this is a device that cannot give PoE power but can be powered up via PoE. So PSE tends to be things that run more in a data center, so switches, power injectors, that type of thing. And the PD, the powered devices, tend to be more of the edge devices, whether you're talking an IP camera, a VoIP phone, a wireless AP, those are all classified as PD devices. Now, it's important to know if you're implementing PoE, if you're going to be needing PoE or PoE Plus, because they're two different standards. PoE was the original. It provides up to about 15.4 watts of power to a PD or powered device. Now, for a lot of devices, that's sufficient. And for the majority of the devices on the market, that's probably all that you're going to need. But there are some devices, so for example, dual radio 802.11n devices that need just a little bit more juice than that. So PoE Plus was developed, and it provides a little bit more than double what the original PoE standard was. So you can get up to 34.2 watts of power. You know, it is important to know what type of PoE standard you're going to need if you have a powered device that's going to take power from PoE. All right, so that concludes our Wi-Fi portion of the presentation. We're going to go ahead and move into cellular and give you guys a quick overview of the cellular technology. Now, there are several generations of cellular networks that exist nowadays. You know, you have anywhere from 2G up to 4G. And there are basically two cellular network standards that exist that each have kind of their own iterations of each of these generations. But really the bottom line is, you know, you can go from the least amount of bandwidth up to the most amount of bandwidth as you increase in your cellular generation. Now this chart kind of gives you a little bit of an overview of what kind of data rates you can expect. So for those of you who are doing some serial over Wi-Fi, if you have a device that is serial based but perhaps doesn't have access to a Wi-Fi network but you still want to give it network access, those types of devices typically use 2G or lower 3G connection speeds because 2G pops up to about 56K modem speed. So if you guys all remember dial-up those days, that's about what you can expect out of a 2G device. 3G is when you start to get into more broadband speeds, and of course 4G with LTE, you're now talking speeds of up to about 50 megs down, which is extremely fast when you're talking cellular technology. So LTE typically, it's a much newer technology for the industrial space, but it definitely is more appropriate for, say, remote video monitoring, that type of thing. So before we get into some more details here, I'd like to ask if you guys have ever used cellular technology at your facilities. I know some of you mentioned that you did in our first poll, but our questions for this poll are, how comfortable are you with cellular technology? First answer is very. I've been using it for a while. Somewhat. I'm just starting to deploy it. Not much. I'm just starting to investigate, and not at all. I have no interest in using it. So looks like we've got some answers coming through, and we might be a little bit more evenly matched on this question than some of the other ones. But it definitely looks like more of you are just starting to look into cellular, which is actually kind of what we've seen in the market. We have cellular is kind of a little bit more of in its infancy in the industrial space than it is in the consumer or the phone space. So here are the results that you guys have put in. So most of you have just started to investigate looking into cellular, which is great. Hopefully we can give you some education in terms of the technology. Next place, looks like you guys have been using it for a while. Some of you have just started to deploy it, and 9% of you say, no, cellular is not for me. So thanks you guys for answering. Some great feedback for us here. So I wanted to kind of show you guys some of the common applications that you may see for cellular technology, and kind of which generation of cellular technology is appropriate for each. So in our first example here, we've got some FTU units that are essentially transmitting small data points back to a central control station. So if you remember all the way back to the beginning of our webinar, we talked about if you need a widely distributed network that doesn't require a lot of bandwidth, that a wide area wireless network is going to be for you. And in the most cases, that is going to be cellular technology, just because there are cellular towers everywhere, and it tends to be very prevalent no matter where you go within the U.S. or even within the world. So in this example here, we basically have these FTUs which are actually operating serially, and that serial technology is very similar to the way that serial over Wi-Fi works. Instead of transmitting over wireless networks, you're now transmitting over cellular networks. However, with cellular, you do have, of course, the advantage that you don't need to actually build up the infrastructure in order to actually use it. It's already there. So it tends to be a little bit more in terms of the cost over time, just because similar to the way your cell phone works, you do, of course, have to pay for the amount of data that you use. But it is a great technology when you're looking at long distance and smaller bandwidth. So serial over cellular, again, perfect for kind of the 2G or the lower standards. So if we start to get into a little bit more data-intensive cellular applications, Something like a variable message sign in ITS space would kind of fit into that bill. So some of these message signs are serial based, some of them are Ethernet based, but they tend to be very widely distributed. And of course, to actually drive out to each one of them, plug in, put in the new message sign, it tends to be a little bit of a pain. So the trend is of course now to outfit each one of these with a cellular modem. And these cellular modems, of course, have the capability of pushing through any kind of data that you want to get into those variable message signs from the central control center without ever having to leave. So it's a great way to kind of make it easier for if any of you are in transportation to kind of get that application going. So which generation is right for my application? 2G, which is something that unfortunately is going to start to go away here in the US, but 2G has typically been used for low bandwidth or any kind of serial-based communications. If you have any kind of I/O points, those of course use very small amounts of data. Those tend to be appropriate for 2G, as well as roadside signs that typically only use SMS to basically change. If you want to move into 3G, if you want to do any kind of Ethernet-based monitoring or programming, so for example, if you have a PLC, an HMI that you want to be able to program or monitor remotely, say because you're not allowed access to the network that it's connected to, 3G cellular is actually a great way to basically backdoor into those devices. It's also sufficient if you want to do like a snapshot monitoring. So 3G isn't great for live video streaming just due to the latency and the low bandwidth, but if you want to take a snapshot of a video monitoring system, say every 10 seconds or every 20 seconds, 3G is definitely an appropriate use of that type of technology. If you want to get into more video monitoring, so if you want to have true video streaming or any kind of higher bandwidth data transfer, you're going to have to look into 4G LTE. And we're very lucky that most providers here in the U.S. have really heavily started to implement 4G across the country. So if it's not in your area already, it probably will be very, very soon. Now there's one kind of, I don't want to say gotcha, but one little thing to be aware of when talking about a cellular network that's a little bit different from your cell phone. Then that is that you have to know what an APN is. An APN is what's called an access point name, and it's basically identifying what cellular network you're connected to. And this is a little bit different because when you get a cell phone, you buy it from the store. It basically comes pre-programmed. You just turn it on and you can use it. But with industrial cellular or cellular modems, you typically will have to implement input the APN into your device in order to be allowed access to the network. And when you get your SIM card from your cellular provider, they will give that to you. But it's just something that you guys should be aware of, that it is very carrier dependent. Now there's two main cellular standards here within the U.S. There's CDMA and GSM. And GSM is one that's more of a global standard. It's used by most carriers globally nowadays. Here in the U.S., both AT&T and T-Mobile use GSM-based networks. Now, GSM has the advantage that if you buy a GSM device, typically you can use it anywhere in the world. But you, of course, have to have a SIM card for whatever carrier that you want to use it on. So it's a little bit more difficult in terms of the setup that you have to get, the SIM card from whatever carrier you want to use. GSM is kind of the, CDMA is kind of the competing standard. It's used predominantly in the U.S. There are a few places overseas that use it as well, but here in the U.S., Verizon and Sprint are the two carriers that use CDMA. So unlike GSM, the information for CDMA networks tend to be basically burned into the device before it's given to you. They don't typically operate on SIM cards, so it makes it a little bit easier in terms of getting up and running with their networks, but you also don't have the flexibility for kind of that global compatibility. So kind of depending on which one you want to go for, that will help dictate what cellular standard or what kind of cellular product you're going to want to use. So if you want to get connected to an M2M cellular network, there are just a few things that you need. We're going to go based on SIM card just because that GSM tends to be the global standard. But there's actually 3 different sizes of SIM cards, and each device that you're going to use may have a different SIM requirement. So it's always important to check which kind of SIM card you're going to want to need. Again, you need to have the APN or the access point name. Your cellular provider may require you to have a username or password, and of course you have to make sure that there's ample cellular coverage. Most locations nowadays are going to have cellular coverage, but of course there are still some rural areas that may have kind of some scattered cellular coverage. Now, the last things that I want to very quickly talk about are ensuring constant connections. So many of you may know cellular is not the most reliable of types of connections. Even nowadays, it's of course becoming more and more reliable as we move into later generations, but it has been known to basically disconnect itself. And when you're talking on your phone, it's not such a big deal. You hang up, you call whoever you're talking to back again. But when you're talking a device that doesn't have the intelligence to be able to do that, that becomes very critical. So you need to have some sort of a technology that can essentially retry a connection if it senses that connection break down or go away. And there are different kind of technologies depending on which vendor you're looking at, but that is a kind of technology that you're going to want to look into having if you're going to be doing any kind of critical data across the cellular network. The last thing is if you are on a cellular network, most providers will give you a private IP address, which is great because it's very secure, but it also tends to be very difficult to access those devices. So you're going to want to have some sort of a private IP solution that will allow you to have access to those devices even if they have a private IP address. That can be anything from a third-party software suite, that could be from the carrier itself, giving you some sort of a VPN or a tunnel connection to your device, but it is something to be aware of. That's kind of an extra step in terms of getting access to your device on a cellular network. All right, so that basically concludes all the information that we gave to you guys. Apologies for kind of rushing through the cellular section. I know we're running a little bit behind, so we're going to try to get some of these questions answered for you guys in the next 5 minutes here. So I'm going to turn it over to Marty. He's going to go ahead and get started reading off some of these questions. Marty?
Great, thanks, Ari. All right, the first question we have here is from David. David's question, or at least he has a statement and a question. So he's using Bluetooth, Zigbee, 802.11g, and N. He's asking, with all of these systems, we have experienced some random nuisance loss of signal that can last maybe as long as 1 and 2 seconds. States it's not acceptable for his application. And wants to know what can be done to minimize these random signal loss events. Any suggestions?
All right, well, thanks, David. That's an excellent question. So from your question, it looks like you're using all technologies that run on 2.4 gigahertz. So if you want to try to help kind of minimize that nuisance loss, I would suggest that you look into using potentially 802.11a or 802.11n on 5 gigahertz, and that should help to kind of minimize some of those. Bluetooth and Zigbee, unfortunately, are known very much to interfere with 2.4 gigahertz systems. So that would be my initial suggestion. You can also kind of do a site survey to see if you still need to use 802.11g and N or 2.4 gigahertz. If you can do a site survey to see if there are any further channels that may be a little bit cleaner than the ones you're using, that could be another option for you as well. All right, Marty?
Great, thanks, Ari. The next question we have here comes from Michael. Michael wants to know, can you explain again if I have a wireless N router and a mix of wireless G and N devices, do the G devices actually hinder the N devices?
All right, that's a great question, Michael. Thank you. Yes, they definitely do hinder. So I talked a little bit about kind of the greenfield versus mixed modes. If you're operating on mixed mode and you have G devices that are going to be accessing an N network, that N access point that's serving all of those devices, both the G and the N devices, will basically have to throttle back to the speeds of 802.11g when those devices are active on the network. And unfortunately, that's the only way that we can, that you can do do it if you're using mixed devices. So if you want to have the true speeds of 802.11n, the best option would be potentially to have two different networks, one that allows 802.11n only, and one that operates on 802.11b or 802.11g. You can do that either by having a device that has two radios, two independent radios. You can set one to N only and one to BG, or you can have two completely independent single radio devices, also one operating on N and one operating on G. And that way you still have kind of that interoperability, but you're still kind of designating a certain network to allow those speeds of 802.11n to kind of take place.
Great, thanks Ari. All right, looks like we're going to have time for two more questions. The first one that we have from Andrew. Andrew asks, I've seen the new 802.11ac protocol, which shows up to 1,300 Mbps. Are there any pluses or minuses regarding this protocol? Your thoughts, Ari?
All right, thanks, Andrew. So yeah, 802.11ac, as you mentioned, is kind of the latest wireless standard. It's one that's just kind of starting to get implemented on the consumer side, but not so much on the industrial side. It's very, very high bandwidth, so it's great if you have super data-intensive wireless communications, which I think we're kind of going to start to see, wireless communications going into that space. But yeah, the biggest plus, of course, is the amount of bandwidth that's available on that protocol, but there's also a little bit more technology built into it that accounts for extra reliability, even more so than 802.11n. So those are kind of the two major pluses of 802.11ac. The problem with 802.11ac is that the channels tend to be 40 and 80 megahertz wide. So as you increase the channel size, you increase the amount of bandwidth that's available to you, but you also decrease the amount of available channels for use. So what happens is that as you get fewer and fewer channels, those channels tend to be more and more crowded, and that, of course, can cause interference. So you just have to make sure that, if you're using 802.11ac and you're using it in the presence of potentially older wireless protocols, you have to just be aware that those very large channels can basically swallow up 1, 2, 3, 4 of some of the older protocol standards. So you can create problems with some of those older wireless networks.
Great, thanks, Ari. Looks like the last question we'll have time for is from Ron. Ron, I believe, was referencing an earlier point in your presentation where you mentioned longer distance. So he's curious if that distance is considered line of sight, and almost like a follow-up or like a clarifying question. Do the antennas need to be able to see each other, or can buildings or hills be in the way? So I'll hand it back to you.
All right, thanks, Ron. That's an excellent question. So yeah, that distance definitely is line of sight. I assume you're talking about the 10, 20 kilometers that we talked about in terms of wireless distance. Those distances do need to be line of sight. Unfortunately, with Wi-Fi, it doesn't have the ability to penetrate buildings. So when you're going those distances, it tends to be good for applications that are kind of outdoors in free space. So whether you're talking down an oil pipeline, if you want to talk to an offshore platform, that type of device, or if you have remote location at the top of a hill or at the bottom of a valley, you have clear line of sight to those, to those areas. That's what Wi-Fi tends to be good for. If you do need to go those longer distances, but you do have buildings or other devices, or other obstructions in the way, you're probably going to want to look at 900 megahertz because that technology has the ability to penetrate buildings. But you do, of course, have the trade-off of that higher bandwidth, just because most 900 megahertz devices tend to be a little bit lower bandwidth. So, it depends. If you have free line of sight, you do need the higher bandwidth. Wi-Fi is definitely appropriate for longer distances. If you do have obstructions in the way, you're going to want to look at 900 megahertz instead.
Awesome. Thank you so much, Ariana. All right, everyone. We are currently at the end of our session. We've had so many questions, so thank you so much. And we've actually had more questions than we have time for. Please know that we'll get those questions answered and respond separately via email. Thank you again, Ariana. Thank you to everyone for your interest and participation. Also, everyone, you'll be receiving a follow-up email with both the recording and presentation slide deck. Lastly, please take a minute before logging off to fill out our survey, as we really value your input and feedback. Thanks again for tuning in, and have a great rest of the week, everyone. Bye now.